All right, we're going to talk about complex numbers today. This is one of my favorite lessons. I always have a lot of fun with this. So I'm going to start you off just kind of easing you into what in the world these things are and trying to convince you how they've been given a terrible name, imaginary, because they really exist. They're just in a plane that we can't see. So we'll get to that. So anyway, I'm going to start with this idea of closure that may be brand new to you, but once I go through it, it'll make perfect sense. It's a pretty simple idea. So I'm going to take 2 plus 3, and that's going to equal 5. All right, hopefully no surprise there. That would be an example of closure. These are all natural numbers, which are countable numbers, the first ones you learn, 1, 2, 3, 4, and so on. And we would say this is closed under the natural numbers, because that's a natural number plus another one equals a natural number. It's closed. So I'm going to make a little number set over here. So natural, and I'm going to put these two together, even though natural and whole are two separate categories. Whole also includes 0, which was a pretty big idea. It took humanity a long time to figure out that could exist. 0 is an idea, infinity is an idea. They're opposites of each other. So let's try something else here. And this is where I'm going to convince you that throughout history, there's been a lot of impossible things that were just as absurd as imaginary numbers or complex numbers. All right, so now I'm going to do another operation. The opposite of addition is subtraction. So let's say I do 2 minus 3. Well, those are both natural numbers, but the result doesn't exist. Or at least we can't subtract two natural numbers and get a natural number out. So for all of humanity, things as unexistent as complex numbers have kind of faced us. We had to come up with ways to get around it. So what do? We came up with this idea of maybe debt was probably the first place it was used, but we introduced the integer numbers. And once you create that set of integer numbers, now you've got something you can actually get an answer to. All right? Fast way to multiply, or fast way to add is to multiply, which is closed under natural numbers. That's okay. 2 times 3 is 6. The reverse of that is to divide. 2 divided by 3. Well, you can't take 2 of something and divide it into 3 equal parts. Well, you can, but it won't come out to be a natural number anyway. So again, we've run into an impossibility. This can't be done until we invented fractions. So that's the next set, the rational numbers. So humanity had to come up with something new, something they'd never seen before, 2/3, a fraction. Now, the fast way to multiply is to raise to a power. And you can take 2 and cube it and get 8, and that's closed under natural numbers. That's good to go. But if I reverse that and take, say, the cube root of 2, well, that's not a natural number, so that can't exist either. We had to create a whole other set. So for a long time, we thought we pretty much had them all figured out. That was our, rather still is, our real number system right there. We had to introduce the irrational numbers. So basically, it's just a never-ending decimal. I'm not going to write that decimal out. It'll take forever. And at this point, we've kind of run through all the natural numbers. So what happens if we start trying to do things like divide integers or divide other fractions? And what will happen is you'll end up finding things that are closed under the real numbers. If you take -2 and divide by 3, well, rational numbers also account for negatives, so that's okay. So we get a lot of things that still work under the real system until we do something absurd like take the square root of -3. There we go. Got something else we can't do. Unless we come up with something, they call it the complex system. So it's just the next step in humanity's march toward figuring math out. Actually, it's a pretty old idea now, but it's just as impossible as any of these other situations. So as you're doing these things, keep that in mind. It's just as impossible as -1 was a couple thousand years ago, or a fraction was a couple thousand years ago. So this idea of math that can't be done, this is nothing new. So I'm going to just kind of stick those out there. For every real number, there's also a complex number that matches up to it. We could say for every real number, there's a complex that maps to it, if you want to say something like that. So it's equally as big as the real number system. I just didn't have enough room to put it there. And if you put all that stuff together, that's your complex system. So from here on out, we will now work in complex numbers. So where are these complex numbers? Well, we can kind of visualize everything else, at least the real numbers, on our normal coordinate plane. So let's try to come up with a visual way to think about that. And we'll get into this more deeper in the year, but I thought I would go ahead and review the I cycle with you and just kind of review that system. So I really just is a stand-in for the square root of -1. We can't take the square root of a negative and get a real result out. It can't be done. We explored that a little bit this year. So I is just a stand-in for square root of -1. You could write that there instead of the letter I. It's just a little bit easier. It's like an abbreviation. Now if I take I and I square it, then that's the square root of -1 squared, which cancels out the negative. Square root of something times itself, you're left with what's under the radical. So that would be -1. Now I cubed, well, let's see, that's kind of like having I squared, because we already figured that one out, times another I. So that would be like saying -1 times I, or square root of -1. So that's going to be -I. I to the fourth would be kind of like saying I squared times I squared again. So -1 times -1, and that's going to equal +1. And it's just going to repeat. Once you get to I to the fifth, it goes back to I to the sixth is -1, and so on. It just repeats itself. So I'm going to back up for a second. And I said, where are these numbers? So I've got to introduce something to you kind of briefly here. Again, we'll get into this more when we get into vectors later in the year. But imagine that this is your normal coordinate plane, your x and y axis. But I'm going to take it and I'm going to turn it sideways so it looks just like a line. All right? So that's actually now the real number plane right there. Now we've turned it so it looks like a line, and you're looking straight out at it. Now imagine that there's a plane for your complex numbers now. It's the exact same way. It's a Cartesian, it's like an x and y coordinate. And we turn that thing sideways like this so that you can see it straight on. Now, that's just kind of an abbreviated way to visualize it. It's a fourth dimensional space now. We just took a two-dimensional space and another two-dimensional space, put them together, that's a four-dimensional space. So this is the best we can do to visualize it. We just can't really, our minds just can't do it. That's a limit our brain has. So think about this though. If your numbers that are purely real are on this line, the numbers that are purely complex are on this line, then we could put 1. Actually, I guess we should start with I to the first power, just I, right here. So this would be basically 1I, and you can go up, you have 2I, and down here you have -1I, -2I, and so on. This would just be 1, 2, your normal way you normally see your numbers. So I to the first is I. I squared is -1. I cubed is -I. And I to the fourth is 1. And we know that cycle just keeps repeating itself. So what you see is when you do the math, sometimes these numbers come into our real number system and they exist in our reality. And sometimes these numbers exist purely kind of parallel to our reality in a fourth dimensional space. And when we get into this more in vectors, you'll see that there's a lot of other areas out here that are not completely in our plane of existence that these numbers exist. So they're there. They're just in a place you can't really see them. All right, so now back to this cycle and figuring out I to different powers. Okay, so I'm going to start you off with this idea of modulo division. If you've never seen this before, I think it's the best way to handle this type of problem. And it's a pretty basic concept. Normally when we divide, we're very caught up with how many times 7 goes into 15. Modulo division is more caught up with the remainder. Okay? So a good example of when you'd want to do this, and it comes up a lot of computer programming. Suppose I want to know what day of the week it's going to be 15 days from now. Well, there's 7 days in a week, so I really don't care how many times I don't really care how many weeks go by if I'm trying to figure out which day of the week it's going to be. I want to know the remainder piece. I want to know how many extra days tick by. That's kind of the idea. So 15 mod 7, the result would be 1. Because if you take 15 and divide it by 7, you get 2, but you get a remainder of 1. And with modulo division, it's all about the remainder. So that's all that is. I'm not going to do much more with it, just kind of giving you the idea. Because that's what you're going to do when you raise I to some bizarre power. Now, really the problems we're going to do, you're never going to see I to a huge power, maybe I to the third, fourth, or fifth power, something like that. But it's always just a good idea to make sure we can handle this just in case you're ever in a situation where it would come up when you you expanded something and you got it to a really high power for some reason. So it's the same idea. This cycle is going to repeat itself every time we go through it 4 times. So if I want to know what I to the 543rd is, I really don't care how many cycles of 4 I have to run through. I just want to figure out what remainder I'm on, where I land. So I'm going to take 543 and divide it by 4, because I could sit here and go, all right, I to the first, all right, that's, I to the second's -1, and I could just sit here and count until I get to 543, but that's why we're going to divide. It's quicker. So I'm going to run through it really quick here. Hopefully this is not too mind-blowing. Bring 3 down, 423 5 times. So here's what it's all about. Here's what I care about right here. I don't really care that I would run through the cycle if I'm counting on my fingers here 135 times. I care about the fact that I'm going to land on the 3rd part of that cycle. So this is the same thing as I cubed, and that's going to be -I. Something else that's going to come up to you is rationalizing denominators when there's a complex number in there. And we've got to rationalize it because really that's a square root of -1. And the process for that was to multiply by the conjugate, so it's still the same thing. A conjugate, it's the same binomial, just with a different sign in the middle. So the conjugate would be 1 minus 2i. And the reason this works out is that whole difference of squares idea. When you take a difference of squares, 2 binomials that are difference of squares, and multiply them together, it's a special case where the first term's squared, the second term's squared, and the middle terms cancel out. So that in the middle term is the piece that's going to have the complex in it. So that's why that's the way to go. And it worked really well for radicals also for the same reason. So multiply it across the top, so 2 minus 4i. And on the bottom we're going to have 1. I'll go ahead and write everything out this time, but if you don't want to write on your homework, I get it. I wouldn't either. So I did inside first. I can do okay. Outside minus 2i, so they're getting ready to cancel out there. And then last, -4i squared. Be really careful with all that. Positive, negative makes negative. 2 times 2 is 4. I times I is I squared. All right, we'll bring it around. Now the top's going to stay the same. Nothing's really happening there. On the bottom, these 2 add to 0, so they're gone. And I squared is really -1. So that's going to be 1 minus 4 times -1. So really 1 plus 4. So final answer, 2 minus 4i over 5. All right, if we were in class right now, I would hand you a piece of paper that had this on it, or I'd just put it up on the board. And I would give you probably about 5 to 10 minutes and ask you to derive the quadratic formula. And I would refer you back to your completed the square work earlier in the year, or earlier in the section. And I would refer you back to your completed the square work from earlier in the chapter. So I'm going to ask you to take a minute and work on this, pause the video, because when you come back, I'm going to go ahead and work it out. So see if you can do it on your own. I would again take about 10 minutes or so. You might hit some dead ends, that's okay. Try something else, give it a good 10 minutes, and then come back and watch the solution. All right, so I asked you to go back and look at your complete the square work because that's going to explain everything you need to do here. So I'm going to follow those same steps. First thing is to get c to the other side. Just get it all out of there. So -c is going to equal ax squared plus bx. And then you always take out whatever's in front of x squared first. So the a is going to come out, we'll factor it out. So a times x squared plus b over ax. That's the only way that's going to check out and be the same, because if I distribute that now, that's good, and that would be b. And once I've factored that a out, I can divide both sides by the a and get it on out of there. And that's what I'm going to do. So -c over a is x squared plus b over ax. Now to complete the square, you take half of this term, so b over 2a, or think about multiplying it by half, might be an easier way to get the b over 2a, and then we square it, and that completes the square. Now whatever, I added that up, I made that, that wasn't there, so I've got to do it on the other side as well. And I'm going to go ahead and square it out. So b squared, and 2a squared is 4a squared. 2 times 2 is 4a squared is a squared. So I'm going to put this part second because it's minus. It really doesn't matter. The b squared over 4a squared minus c over a. And now we can reduce this back down to a perfect square binomial. So x plus b over 2a squared. And the shortcut to that, it's going to be just x in the beginning, half of this term on the bottom. And if you need to, you can always FOIL it out and check. This would be x squared. You would have 2bx over 2a, which when you add those together, you get 1bx over a. And if you squared the second part, you get b squared over 4a squared. So you get this. It's going to be good. Now over here, I really need common denominators, so I can combine these. This one still needs a 4 and another a. So if I multiply by 4a on the top and the bottom, think about what that would give me. So it's going to be b squared minus 4ac. And on the bottom, both of these would now be 4a squared. And that should be looking familiar now, b squared minus 4ac. So over here, x plus b over 2a squared. And I want to get x by itself. That was the goal, so I'm going to take a square root on both sides. Can't really do much to the top part here. That's going to stay underneath the radical. B squared minus 4ac. That's looking even more like it. I did take a square root, so it is plus or minus. Then on the bottom, the square root of 4 is 2, and the square root of a squared is a. Plus and minus being up there, I mean, you could put it in front of the whole fraction if you want. It really doesn't matter. Now over here, the squared is now gone. So x plus b over 2a. And finally, to wrap it up, I'm going to subtract the b over 2a. Because again, I want x by itself. And that should do it. There's your negative b. Everything can be over 2a because we can combine these two fractions. So negative b plus or minus the square root of b squared minus 4ac. And that's going to equal x. And there it is. That's your quadratic formula.